All right. Hopefully, we'll also upload this stuff online so that you can see it. So as we were discussing that, we talked about in the first week and also in the previous class, we talked about um, how solid state material and its property is dependent on the atomic structures. Okay, the way you arrange the atoms, it pretty much defines that how the electron is going to be propagating through the structure. So this is why we spend some time to understand that in how many different ways we can arrange an atoms. And we gave some examples. For instance, we talked about few possible structures of atoms. The silicon atom, it looks like the left-hand side. It's called diamond structure, where you can see that in a cube, on the all 8 corners, you have 8 atoms. And also you have some atoms on the faces of the cube, and also some atoms in the interior. So from there, we also discussed that how we can find out what is the atomic packing density of atoms, like how many atoms are there inside that cubes. We also discussed that how to calculate the density of atoms on a surface, right? And we also talked about that how to define a plane, particular plane in an atom. Um, For instance, we talked about how to define different planes on a cubes and how to name them. There is a specific way of giving the levels on an atoms. So most likely in the homeworks, I will give you some problems where you have to solve the atomic densities on a cubes or atomic densities on a planes or defining and naming the planes, etc., etc. All right. And do you remember that why we talked that defining a plane is important? It's because when you look into different planes of a cube or other atomic structure, the atomic density changes. Okay, if the atomic density changes, then the electron propagation property also changes. Okay, for instance, I'm repeating this especially for people who are taking here for the first time. Um, For instance, if you look into a plane which is shown by the blue color here on the left-hand side, um, and if you calculate the number of atoms on the blue plane versus number of atoms on the green plane, you will see that the density of atom is different because the size of those planes are different. So this is why we need to understand that how different planes in a crystal has to be defined. Okay, the video is uploaded online, so please take a look at it. Um, so today we will start to discuss about the quantum mechanics and the most basic things about it. So first of all, why we need quantum mechanics? We talked about the atoms, the arrangement of atoms in a crystal. Now, remember that in our current course, the main objective is to find out the propagations of electrons. Okay, how easily an electron can flow through a material. So in order to understand the electron flow through a material, why do we need quantum mechanics? We have actually a very simple law that explains how atom flows, how electron flows in a material. And it's actually Ohm's law, right? V equal to I multiplied by R. So if you want to calculate the current through a material, you can simply use this formula. Let's say you want to calculate the current through a copper wire. So you have to find out the resistance of the copper wire, and it's also easy to find out. The resistance pretty much depends on what is the length of the wire, what is the area, cross-section area of the wire, and also what is the conductivity of the wire. So based on that, you can find out the resistance, and then given a particular voltage, you can find out the current, right? So there is no quantum mechanics here, right? It's as simple as that. The problem is this thing only works when things are pretty big, like when you were talking about electron propagations in a big piece of wire. But this is not really true if you try to see what is the electron propagations in few nanometers of material. Okay, then this thing actually totally breaks apart. It simply doesn't work. Okay, so this is why we need to understand that how we can explain the electron propagations and currents in a very small device. And for small stuffs, quantum mechanics is the way to go. Okay, so quantum mechanics starts from the very basic stuff, the atoms. You know how an atom looks like an atom has electrons, an atom has protons, and also neutrons. On the very center, it has nucleus. The nucleus contains all the protons and neutrons, right? Protons are positive charge. And on the outskirt, on the periphery, it contains electrons. So now the question is, electrons are negative charge, right? And protons are positive charge. So if I put a negative and positive charge close to each other, what's going to happen? They attract each other. So don't you think that if I put electrons um, a little bit away from the nucleus of protons, shouldn't they just come closer to each other? Shouldn't they just collapse? Like if they really should attract each other, then shouldn't there be any existence of atoms? How come electron can keep away? There is no wall, right? There is no hard boundaries that is keeping them away. So why electrons is not coming close and just falling into the nucleus and just whole atoms should get destroyed? What do you think that keeps electrons to do that? Any thought? Or have you ever wondered about it, that why electron is not just coming close to it? Mm-hmm. Okay. Actually, that is partially true, that is partially true. That so what he's saying is that if we have um, some protons and we have some electrons, let's say some electrons are here and a little bit away, some electrons are also existing here, then it is possible that these electrons at the very outskirt, it's not feeling actually all the forces from the protons, because force, the attraction force from these protons is being cancelled out or is being reduced by the other electrons. Is that what you are referring? Hmm. Hmm. Yes, yes, exactly. So because these guys, they have all same kind of charge, they're actually pushing apart each other, right? So that's what you are referring to, right? Yes, actually that's partially true. But why partially is why it is not exact truth is the following, that I understood that these guys are actually pushing them apart. But how about the nearest electrons, which are closest to the nucleus? That shouldn't that just fall into the nucleus? So there must be something that is keeping them apart from each other. So think about when people first looked into this model, they thought that maybe it acts like the planetary system. So in a solar system, you know that Sun and Earth, Mars, everything, they pull each other together by gravitational force, right? But still, we are not falling into the sun. Why we are not falling to the sun? They are spinning, right? So because they are spinning, they create a centripetal force. Okay. So when sun attracts the earth spins, and because of the spin, the centrifugal force is going to be cancelled out by the centripetal force. If you spin something, you will immediately notice that this object is trying to get away from you. Okay, so in the similar way, this centripetal force, because of the spinning, is being cancelled out by the centrifugal force of the gravity between sun and the earth. So people thought maybe this is the answer. Maybe electrons are not just staying there still, maybe they are rotating. And that's why they are not actually falling into the nucleus. That might sound interesting, but there is a problem actually in this explanation. The problem is the following. An electron has a negative charge, right? So when a charge moves, moving charge means it's accelerating. You know all these things? Even a charge has the same velocity, but it keeps moving. This means that it changes its directions every time. This means it is accelerating. If a charge accelerates, then it radiates. You know how antenna works? All this mobile phone works? It's because inside your mobile phone, there's an antenna, and in that antenna, we create some waves to oscillate. Okay. So when actually those are waves of electrons. So when the electrons oscillate, they radiate the signals. And this is how you propagate your informations. Understood? So people also knew that this is going to happen when electron is going to rotate around it. So if electron rotates, this also should radiate some energies, right? If it radiates something, it should lose energy, and that means its velocity should reduce. Remember that the energy is half mv square, right? M is the mass and v is the velocity. So half mv square is the kinetic energy. So if you radiate, you lose this half mv square energy. That means your m is constant, mass is constant, so v must be reduced. So it means that since the electrons is negative charge, its velocity as it keeps moving, it should reduce. Remember that Earth, the velocity of Earth doesn't reduce. Why? Because it is not charged, right? Earth is neutral. But in case of electron, this is not neutral. It has negative charge. So the idea of the planetary system doesn't really hold here because the electron has charges. So it must radiate and lose energy, and eventually it should fall down all to the nucleus. So this idea actually is not also true. Okay, although it sounds very interesting. So there must be something else that is really preventing electrons from falling behind. Remember that if we cannot explain that why electrons stays, then all of our knowledge actually just start to contradict each other. We cannot even explain that why we exist. No atom should exist. So there is something definitely interesting going on here. And let's try to understand this. So quantum mechanics, it actually saves us. It said that electrons, which you are thinking to be like a particle, like a solid ball, it's actually not a particle. Quantum mechanics says electron is actually a wave. Okay. So, okay, I mean, quantum mechanics says it's a wave, but how it really solves the previous problem that we have a attraction force between electrons and protons, but still electron doesn't come close to the nucleus. Uh, in order to understand that, let's keep some patience because now we are going to discuss something that is really head twisting phenomena. Like people argued over it for years, and we actually needed the best of the best scientists to come up to this particular concept. So bear with me, and we'll go through them one by one. We said that an electron inside a atom behaves like a wave. So let's first try to understand that what is the behavior of a wave versus what is the behavior of a particle. A particle, probably the most simplest thing, a particle has mass. Okay, any particle has a mass, and a particle has momentum. Momentum means it's a multiplication of mass and velocity. Okay? So all particles has mass and momentums. And the second thing is a particle is discrete. Okay. So here is a particle, here is a particle. You can define that these are the particles. Okay. In case of wave, a wave doesn't have mass, right? A wave has instead frequency and wavelength, right? So you cannot really say that a particle has a frequency. It doesn't mean anything. Like, what do I mean if I say that this guy has a frequency? It's just meaningless. But in case of wave, we can talk about the frequency and wavelength. So this is one big difference between particle and wave. The another big difference is a wave is continuous, okay? Whether a particle is discrete. So how is it possible that these two things, which are very different from each other, how come an electron, we know that electron has a mass, how come electron can behave as a wave? So people understood that electron is a wave and a particle much later. But at the very beginning, people started to understand that light itself can be a particle and a wave. So let us see that how people came to realize that light is a wave. So one big difference between a particle and wave, I say that a wave has a wavelength and a frequency. So let me ask you this. Um, Give me an example of wave that you know of. Don't say electron, because give me some example that you already know and you are certain that this is an example of wave. What is an example wave? Say it out loud. Right, right. So the waves that is going out from your phone is definitely waves. So it's an electromagnetic radiations, right? Any other example of wave? Same thing, radio waves. Lasers, so lights. All the lights, these are actually waves. Okay, yes. Oh, fine. The vibration. So this is another example. It's a mechanical wave, right? So all the previous examples that you gave, these are actually electromagnetic radiations, the radiations from phones or the lights. This example is a radiation is an example of mechanical waves. Okay. Any other example? Sound. Very good. So I said that the a wave has a property which can be defined by its frequency and wavelength. Okay. Now you just say that these are the examples of waves, but how can you prove it? Like, is there any direct way to say that it's really a wave, light is a wave, or sound is a wave? There is actually one way to know that whether something is a wave or not. And the idea is that since a wave has ups and downs, if you superimpose two different waves, it doesn't necessarily going to increase the wave. It's possible that upon superposition, these waves can destroy each other. Just think about this, that if I have one light, but if I have two lights in this room, and the total brightness of this room is going to increase, right? It's not going to decrease for sure. But these lights are not actually coherent light. Like coherent means they do not have the same frequency. They have actually a range of frequencies. But if you can somehow make a source which has a very single, well-defined frequency and wavelength, then you can see the behavior of interference and bit. So I will give you an example where you can see the behavior of wave. So one example is probably this, the water waves, right? You can see that if you have two drops um, of, of objects on the water surface, they create these kind of concentric circles, and they start to interfere with each other and create this beautiful pattern of interference. But we talked about sound wave, right? So let's see if we can really prove this sound is a wave. Okay. Remember that we just knew sound is a wave, but how to prove it? So let us see. So I said that since if something is a wave, if you add them together, it doesn't mean that total wave is going to increase. It can also decrease, right? So let's say I take a sound box and I take another sound box, I add them together. It may not really increase the sound. It can also decrease the sound. So to give you a proof, here is one example. So I'm going to generate a tone, and let us see how it sounds. Okay. So let's see. Everyone can hear it, right? It's a little bit painful, but just bear with me. So I wanted to prove the point that if you add two different sounds, it's not just going to increase the noise. It might do something very interesting. So let's add another tone. So now I added two tone, right? Both of them have same frequency, 440 hertz. But what if I change one of their frequency just a little bit? Let's say instead of 440, I increase one of their frequency by 1 hertz. Tell me, what do you experience? Increases and decreases, right? So this could not be possible. This could not be possible if it were just a particle. Remember that if you throw two particles, of course it is going to make things more crowded. But if you throw two waves that can even destroy themselves or increase themselves, okay? So that is the direct proof that something is a wave. Understood? In a similar way, we can also prove that light is also a wave because light can interfere. Okay, if you have you heard about Young's double slit experiment? So Young's double slit experiment, it says that if you uh, take a light and let me go back. So Young's double slit experiment, it shows that if you take a light and pass that light through two different holes, slits, and let them interfere with each other, it creates a diffraction pattern. And the diffraction pattern is being shown here. So they take a light on the left-hand side, these lights passes through two holes over there, and then all those lights, it falls on a screen. And on the screen, if you assume very naively, you may say that, well, since the lights are coming from two different slits, probably you will see two different um, light strips, right? That's our common assumptions. But instead of seeing two different light strips, we're actually seeing a multiple of lights and dark fringes, okay? Just like this following, this guy, okay? And it's because all these lights, they're actually interfering somewhere, and they're actually either interfering constructively or interfering destructively. So this is why instead of just having two bright spots, we're having a multiple of bright and alternating bright and dark spots. And this is exactly what we have just experienced in terms of sound. In terms of sound, we have seen that it increases and decreases with time. And we can also show that it increases and decreases in space. Understood? So that is a direct proof that something is a wave. So Young's double slit experiment first proved that light is a wave for sure. But then some crazy guy named Albert Einstein, he spoiled the party. He said that actually light is a particle. How? Um, and the idea is the following. Before Einstein came, quite some time for a while, people knew about an interesting effect called photoelectric effect. Okay. So what is photoelectric effect? It means that if you shine light on a metal, then some electrons is supposed to come out. Okay, you know that metal is full of electrons. There are a lot of free electrons in metals. So if you shine light on metals, people have observed that electrons come out. Okay, so if electron comes out, the metal will become positively charged, right? So people can measure. I mean, people cannot see electrons, of course, but people can measure its voltage. So by measuring the voltage, people knew that it lost some electrons when you shine some light on it. Okay. Now the problem is that part is not a problem. Like people understand that maybe light has some energy. So if you bombard something with something else, then it is trying to kick off, knock down the electrons. So if if you inject light on a metals, probably because of the energy, some of the electrons they are actually knocking off from the metal. The problem is, according to the classical understanding, if you shine more light, then you should see even more knocking off of the electrons, right? But that's not true. Uh, for instance, I'll show you one demonstration. That's a very nice YouTube demonstration that I found very recently. And if possible, probably we would do it in classroom. Um, but for now, let's just see the effect in reality.
How much time do you spend writing at work?
A few hours a day.
So I have work-related trivia questions. How many hours a week does work?
Hey, everyone.
All right. So the video is a little bit long, so I will try to only show you what's really important. So this guy.
Today I'm going to be showing you that light is actually made out of small little particles. I'm going to be showing you the photoelectric effect. This device here is called an electroscope, and what it do is it measure the amount of
maybe
my hair, and they're stuck on the balloon now, so I can wipe them onto the plate.
Maybe I can just make him silent and just show you from the picture and explain that what is going on here. So this is something called electroscope. Okay, an electroscope is something that can deflect the compass if you apply some voltage over there. So this guy is trying to create some charges on the disk on top, and if there are some charges, this compass is going to deflect from its original position. So he did that, and so you see that the composite moved, and because of this balloon, this guy is going to have some negative charges. Okay, and now the point is that if you can somehow knock it off some electrons, then this compass will come back to its previous position. Remember that when you charge the balloon and touches this disk, you created some extra negative charges. So now let's see that by applying light, whether we can knock off those additional charges and bring back that compass to its previous position. So how to shine light? So he tried this. He tried one light. You see that this light is a white light. It's a visible light. So visible light has a wavelength of maximum 400 nanometer. Okay. This is the blue light, and 700 nanometer corresponds to red light. So he gave this light on the disk and tried to see that whether this creates any kind of deflections on the compass. But apparently nothing happens. Okay, he created really, really bright luminous light. Nothing happens. So then he tried this. He tried a different light of a different color. Okay. So this is a UV light, which has a slightly higher frequency and smaller wavelengths. Okay. So this time, he also tried to illuminate the light and see what happens. Nothing happens so far. So now at the third time, he took another light, which has 250 nanometer wavelength. It's even smaller wavelength and even higher frequencies. Okay. So the previous one, the very first one, was white light. It has the longest wavelength, and this guy has the shortest wavelength. Okay. So for the shortest wavelength and the highest frequency, let's see what happens. The moment he shines the light, it's not very bright, but do you see that the deflections of the compass? Do you notice that? So it comes back to the previous position. So it shows that it's really not about the energy, but something is going on with the color. Okay. And this is where people started to guess that maybe color has something to do with the energy. Okay. Previously, people didn't know that. And they actually come up with this formula that the energy of light is related to frequency like this. So H is called the Planck's constant. And nu is called the frequency. Okay. So, and then there is a factor of n. N is actually number of particles. Okay. So they came up with this formula that maybe light actually follows this formula, E equal to n multiplied by h multiplied by the frequency nu. So if this is true, then you can show that actually energy is dependent on frequency. So what happens here is the following, that when you shine with a white light, although you are shining with a very bright light means you are increasing the number of n, okay? You are increasing the number of n. But nothing happens, no electron comes off from the metals because each of these uh, all the energies there actually comes in the form of discrete packet. Okay, so think about this, that instead of sending a continuous energy, you are sending energy in terms of small packets. Each of this packet has an energy of h multiplied by nu. Okay, and each packet can only knock off a single electron. So even though you are sending a lot of packets, only one packet can interact with one electron. So if you have your frequency to be very low, then although you are sending a lot of packet, it will not be able to knock off any of the electrons because each of the packet has a much smaller energy that is needed compared to the energy that is needed to knock off the electrons. Do you follow? So then they changed their color. Color means they are changing their frequency. They make the frequency go higher. And this time, when they used a UV light, they showed that now, even with a very modest amount of light, they were able to knock off the electrons. Because now they're sending the packets, and each of the packets, because of the higher frequency, each of the packet of the energy, it contains more energies. Okay, so each packet, when it when it bombards on the electron, it can knock it off. So this is where people first got the idea that maybe energy is not continuous in a light. Energy is discrete. So I said in the beginning that the property of particle is that particle is discrete. A wave is continuous. Okay, one of the biggest difference between particle and wave. But now people realize that actually these energies, well, in a big scale, when you talk about the macro scale, it looks like continuous. But when you go to very small scale, like subatomic scale, it is actually not continuous, it is discrete. Okay, so when you talk about the radiations from mobile phones, it's okay to think about everything as a continuous, it's fine. But when you talk about the quantum scale, these are not actually continuous. This is all discrete. Okay, why these are all discrete? I'll give you an idea that why it doesn't matter when you talk about radiations from an antenna, but why it matters in a small scale. If you look at the value of h, let us do some calculations here. I'll write it over there. So let us try to find out what is the energy in a given packet of blue light. Okay. How to calculate the energy in a blue light packet? You have to multiply h with the frequency. Now the value of h is actually, if I remember, something like 10 inverse 34. And the frequency of light, let's say blue light, is if let's say this is the velocity of light, 3 multiplied by 10 to the power 8, and the blue light has a wavelength of 400 nanometer. So 4 multiplied by 10 inverse 9. Okay. So if you can work it out, you will just look at the exponent of 10, and you will see that what is this guy? This is 8 plus 9, so it is 17. So it's actually 10 inverse 17 joule. Okay, 10 inverse 17 joule is a very small value of energy. Okay, very small value of energy. To compare that how small the value of energy is, what is the wattage of your cell phone? Like how much power, or what is the wattage of your laptops? Do you know how much watt it consumes each second? How much energy is consumed each second? It's roughly, I think. So let's say you are running it with 100 volt, and it roughly carries 1 ampere current. So we can calculate the power, voltage multiplied by current. Voltage is 110 volt. This is the voltage of the line, and multiply by 1 ampere current. So this is roughly 100 watt. Actually, it is even less than that, something like 40 watt. Okay, 40 watt means in each second, the laptop consumes 40 joule of energy. Okay, I think your mobile phone, it also consumes something like 1 watt. Okay, that means in 1 second, it consumes 1 joule of energy. Versus look at this energy, 10 inverse 17, right? So it is not even 1 joule per second. It's, you divide the value of 1 by 1 followed by 17 0. It is that small. So this is why when you look at the radiations from an antenna, it really, this scale doesn't really matter. Okay, that's why it's okay to just consider everything as a continuous value. But when you look at the quantum scale, then this small value becomes very important. Does everyone follow? That why when we take the other courses, like if you have you taken a course on electromagnetics? Okay, so it's okay if you have not taken it. So in those courses, they do not talk about the quantum properties. We explain everything as a continuous wave. Okay, but later on in this course, you will see specifically that it's actually all discrete. Energies comes in the form of very small packet. Each packet contains a very small amount of energies, and it depends on the frequencies. Does everyone follow? Okay. Are we running out of time? Or we have a couple of more minutes? Oh, okay. Almost we are done, right? All right. So let's call it a day. And so hopefully we will meet again tomorrow. Not tomorrow. We'll meet again on Monday, right? Same time. All right, guys. So I'll see you. Take care.